So today we're going to look at another lesson in Unit 2. This is going to be Lesson 4 of the Library of Functions. Also, it's going to deal with what we call Piecewise Defined Functions 3.4. There's 9 basic graphs that we want to focus on. So in this assignment, we're going to try to become familiar with several functions and their graphs. So what we're going to kind of see is these functions are going to be called what we call our parent functions and everything. So our goal really is going to be by plotting 3 points and just knowing what the shape looks like. We're going to try to be able to graph these 9 functions that we have before us. So this first function is called the identity function. Identity, basically what this means is the y value and the x value are the same thing. So notice how we have f of x. F of x also stands for y equals x. So whatever y is, or I'm sorry, whatever x is, y is. So identity just means the x value and the y value are identical. Identity. So if I have a -1, I have a -1. If I have a 0, I have a 0. If I have a 1, I have a 1. So -1, -1, 0, 0, and 1, 1 is kind of what that means just by recognizing identity function. Now, if I want to actually evaluate ordered pairs, remember the x's are what our domain is. So if I want to evaluate f of -1, -1 goes in for x, and you end up with -1. So -1 goes in, -1 comes out. F of 0, 0 goes in and 0 comes out, because all you're doing is replacing the x with a 0. F of 1, notice again, you're just putting 1 in for x, so you just have 1. So from a graphing perspective, you have this -1, -1. You have this 0, 0, 1, 1. If I want to continue on, it would be like 2, 2, 3, 3, 4, 4, 5, 5. So notice how it really does create just this slant line. So if you see the function f of x equals x, just remember that it's really just this slanted line that goes to the origin. So if I want to try to graph this, see if I can make a sketch of it. So I graph this thing. Let's see here. It should just be a kind of a line that passes through those points. So that's what the graph kind of takes on, is that look there. So some things that we want to pick up on as we keep talking about is, first off, let's talk about the domain. So the domain, again, remember we look for the left bound, and also the left bound is an arrow and the right bound is also an arrow. So there aren't any domain restrictions. So the domain is described as -infinity to infinity. As far as the range goes, the range, again, if we look at the lower bound is also this arrow, and the upper bound is also this arrow. So from a lower to an upper, there aren't any range restrictions. So the range would be from -infinity to infinity. Intercepts, what we're referring to there is where it crosses the x and the y axes. So where does it cross the x and y axis? So notice that it crosses both the x and y axis at the same exact spot. It crosses at the origin. So the x-intercept is going to be 0, and also the y-intercept is going to be 0. As far as symmetry goes, one of the things we pick up on is symmetry. Let me get rid of these circles on the ends. So as far as symmetry goes in our problem, notice how there's this 1, -1, I'm sorry, this 1, 1, and it notice how reflected over the x-axis, I'm sorry, over the origin, there's this order pair -1, 1. So notice how there is this point reflected over the origin. If I look at the points, say 2, 2. Notice that there's an ordered pair on the other side of the origin at this -2, -2. So notice how, again, we have this reflection over the origin. So this does have symmetry. It's symmetric with respect to the origin. Again, in origin symmetry, if the order pair XY exists, then the order pair -X, -Y must exist. So notice how we had the order pair 2, 2 existed, and also how we had a -2, -2 existed. So we can continue that on with quite a few points, that mirror image. So an identity function actually does have symmetry with respect to the origin. The next function we have is what's called the constant function. A constant function is going to be a horizontal line. So remember, when we talk about the constant function, you know how we have this f of x here, but that's the same thing as y equals -2. So what this is saying is it doesn't matter what x is. So when x is -1, y has to equal this -2. It's constant. When x is 0, y remains constant. It's still a -2. When x is 1, y remains constant. It's a -2. So from a graphing perspective, we have this -1 and we have this -2. We have this 0 and we have this -2. We have this 1 and we have this -2. So notice how the y values are remaining constant. So a constant function is basically when f of x is just equal to a number. We call that number a constant. So from a graphing perspective, what we have in is this horizontal line that goes from here over to here. Just keeps going that direction. So that's what we mean by a constant function. It's going to be a horizontal line passing through that y value. So really all we need is that one order pair to graph it. So really all we really need is that y-intercept, if you will. So as far as domain goes, if we look at this problem here, domain, the domain, notice how the left bound is a arrow and the right bound is an arrow. So there is no domain restrictions. It's just simply -infinity to infinity. But as far as the range goes, the range, there's only one y value. Y value is it's always a -2. So our range, we can say the set of x's such that x equals -2. That's all there is. As far as an interval, there really isn't an interval here. So, and I shouldn't have said x, I should have said y. Sorry about that. Range involves y, not x. So sorry about that. So if I'm using that notation, I should be using the letter y. So the set of y's such that y equals -2. So really there's only one range value, and that's a -2. As far as intercepts go, notice that it's parallel to the x-axis, so there's not any x-intercepts, but there is a y-intercept at this spot right here. So the y-intercept is going to be a -2. In symmetry, notice how it does get reflected over the y-axis. So we see that there is y-axis symmetry. So notice that when there's an order pair xy, there's also an order pair -xy. So that means we notice how we have the order pair, say 2, -2. So this 0.2, -2. Notice that we have this other order pair where we have now the x is changing -2, but the y value is changing the same. So notice how we have this point here, and then over on this other side, we have this mirror image of it at this spot here. So those two spots there, we see this reflection over the y-axis. The next function we want to talk about is what's called the square function. A square function, we also call that quadratic. It's because that's a second degree function, or we call it quadratic. It's going to kind of take on this, what we call a U-shaped curve. It's going to be more of a curve. What it's going to do is it's going to run along the x-axis. This is also called an even function, okay? So this is going to be an even function. So keep that in mind as we move forward. So when I do f of x squared, notice that your x value is going to be squared. So if I put a -1 in, you're going to have this -1 squared, which is going to actually be a +1. F of 0, 0 goes in and you have to square the 0, and that's going to give you a 0. F of 1, if you put 1 in, you're going to get 1 squared, and you're still going to get 1. So -1 was, when I did the calculations, I got a 1 as the output value, or the y value. 0 went in, I still got 0, and then 1 went in, I still got 1. Some additional values to kind of pick up on is, notice if I pick, say, 3, I'm going to get a 3 squared, which is a 9. If I pick a -3, -3 squared is going to be this 9. So if I graph this, I have this -1, 1. I have this 0, 0, and I have this 1, 1. We also, if you want to graph an extra one, this 3, 9 would be up here, and this -3, 9 would be over here. So if we look at this graph, it kind of comes down, it starts to bend a little bit, and it kind of curves in and makes this little U-shaped curve. So over here, same thing, it's coming down, then it's kind of bending and turning and going back up. So we have what we call this U-shaped graph. So when graphing it, all we really need to know is the origin is 0, 0, and then there's this point 1, 1, and also there's going to be this other point reflected over the y-axis, this -1, 1. So notice how the x value here is negative, and then this x value here is positive. Notice how that's that reflection. So when I graph this point 1, 1, there's going to be this point -1, 1 reflected over the y-axis. Similarly, if you notice this point 3, 9, I have this 3, 9, and notice that there's this -3, 9. Notice how, again, the x value is changing. So this 3, 9, and then reflected over the y-axis is this -3, 9. That's what we mean by y-axis symmetry. So as far as just answering a few other questions over here, let's talk about domain. Again, the domain, we're looking at the left bound, which notice how, again, it's an arrow, and the right bound is an arrow, which means there's not any boundaries. So that's just going to be -infinity to infinity. The range, on the other hand, if you notice here on the lower bound, there is a lower bound. There's that value right there. Notice that at that spot there, y is equal to 0. So my lower bound is my y value is 0. And then if you look at the upper bounds, there's these arrows on the upper bounds. So what this means is you include 0 as your lower bound, but it goes through infinity on the upper bound. So there is a lower spot, but not an upper spot. When it comes to the x and y intercepts, notice that the graph does pass through the origin over here. So that's just that one spot. So the x-intercept would be 0, and the y-intercept would be this 0. And as I said, the symmetry is this y-axis symmetry. It is reflected over the y-axis. Notice, as we said, if x, y exists, then there should be an x value that's opposite in sign across the y-axis. So the y value doesn't change, but the x value does. And that's what we call y-axis symmetry. The square root function, kind of what it means is, I think what I meant is right arm up. So this graph here, it kind of opens to the right. It's a right side curve, and it runs along the x-axis is how this is going to play out if we graph it. For us, we're just going to graph a few points. If I evaluate f of 0, we just get the square root of 0, which is still just 0. If I evaluate f of 1, the square root of 1 is just still going to just be 1. If I evaluate f of 4, now the reason I chose 4 is the square root of 4 is actually 2, so that's why I chose that. So if I can remember that, 0 is going to be 0, 1 is going to be 1, but 4 is actually going to be 2, and that's where the bend starts to occur. the curving. Notice here, you cannot take the square root of a negative number. So there is a domain restriction. You cannot pick a value less than 0. So when you graph this, 0, 0 is going to be the furthest point to the left. 1, 1 is going to be here, and 4, 2 is going to be here. And this is why this graph kind of starts to run along the y-axis. It kind of bends like this. So it's kind of a right arm up, if you will, kind of bending to the right side curve, if you will. So that's what a square root function is going to look like. So the square root function, notice how it does have a domain restriction. You cannot go left to 0 because you cannot take the square root of a negative number. So the domain is actually going to be 0 to infinity. Notice how there is this left bound of 0 for x, but the right bound, there is not one that's an arrow there. The range is very similar. Notice how, again, as far as the range goes, the lowest point is this 0 again. And again, it's got this arrow on the upper bound. So the lower bound is 0, and the upper bound is an arrow. So as far as the range goes, it's 0 to infinity. Intercepts, again, they're both at the origin. So we would describe the intercepts as simply x equals 0. The x-intercept would be 0. And the y-intercept would be this 0 because that's the origin. That's the spot here where x is equal, y equals 0. So that's your x-intercepts. Symmetry. Notice for x-axis symmetry, if there's this point here, say at 4, 2, there's supposed to exist a point 4, -2. This point does not exist. So there is not any x-axis symmetry. Notice how 4, 2 exists. So there should also have been a -4, 2. This point over here should have existed for y-axis symmetry. That's not happening. For origin, if there's this point 4, 2, there should have been this point -4, -2 over here. There's not this point either. So this does not have any symmetry. There is no reflection across the x-axis. There is no reflection across the y-axis, and there is no reflection over the origin. Okay, so that's what we have there on that. So that's what we call the square root function. It's kind of like a half a U opening along the x-axis instead of the y-axis. The next function that we need to get familiar with is what's called the cube function. It's snake-like, and it's going to kind of run respect to the y-axis. And this is going to be an odd function as well. And remember, odd functions are going to be symmetric with respect to the origin. So notice how, again, if I evaluate this, f of -1 is going to be -1 cubed. But remember, if you raise a negative number to an odd exponent, I'm going to still get a negative number, so it's going to be a -1. F of 0, that's going to be 0 cubed, which is still going to be just 0. F of 1 is going to be 1 cubed, but 1 cubed is still going to just be 1. If I want to pick another point, I could say f of 2 would be 2 cubed, which would have been 8. And f of -2 would have been -2 cubed, which would have been also a -8. So what we're really going to pick up on those, we're just going to try to graph this -1, -1, 0, 0, 1, 1. That's the main 3 points that our goal is to pick up on. But if you want to graph more points, you can. Our goal is to plot just a few points and just kind of recognize which way it goes. So I have this -1, -1, 0, 0, 1, 1. And just for good measure, 2 gave me 8, and -2 gave me this -8. So pick up on as far as the graph goes, this graph is kind of going to come down, and it's going to kind of bend and turn and snake around here, and then go back through this other point here. It's going to look something like that. So it's kind of going to be the shape of that graph. It's kind of what we call like a snake. Kind of slithers around there like you'd see on the ground. So as far as the domain goes, the domain, notice how there is not a left bound and there is not a right bound. Those are arrows. So that means the domain is -infinity to infinity. Similarly, The range, notice how there's an arrow on the lower bound and there's an arrow on the upper bound. So again, there is no range restrictions here. It's negative infinity to infinity. Intercepts, again, it's just that origin. The origin is the only place that it crosses both axes is this spot here. So the x-intercept is going to be 0 and the y-intercept is going to be 0. And this does have origin symmetry. It's an odd function, so it's got origin symmetry. Notice how if there's this point xy exists, then there's got to be this point negative x, negative y has to exist. That's origin symmetry. So notice how there is this 2, 8, and there's also this -2, -8. So what we're seeing is these points are reflecting across the origin. So if you notice this point up here, 2, 8, if you go diagonally across that origin, you're going to see this reflection of this -2, -8 down here. And that's what we mean by origin symmetry, is this reflection across the origin. The cube root function is also going to be snake-like. So it's kind of look like the cube function, but the cube root function is going to run more along the x-axis. So as I graph this, again, if I just pick some ordered pairs, -1, 0, 1, if you notice, those are our main ones. I can evaluate f of -1 rather easily. The cube root of -1 is actually going to be -1, because -1 times -1 times -1 is -1. F of 0 means the cube root of 0, because 0 times 0 times 0 is 0. F of 1 is going to be the cube root of 1, but that answer is 1 because 1 times 1 times 1 is 1. Now, if I'm doing cube root, another one would be probably to pick like an 8. The cube root of 8 would actually be a 2, because 2 times 2 is 4 times 2 more is 8. So that. Or if you chose f of -8, I can do the cube root of -8, because that would also be a -2. So again, what we're picking up on though is we're just going to try to graph 3 points: -1, -1, 0, 0, 1, 1. So if I plot those points, -1, -1, 0, 0, and 1, 1. What I should pick up on, it's going to run along the x-axis, but having these other points are not going to hurt us. To have this 8, 2, and this -8, -2 can kind of help us out as well. So when 8 went in, 2 came out, -8 went in, -2 came out. So what we kind of see is this graph kind of takes on this look here, is it kind of runs more along the x-axis and then kind of bends and stakes, if you will, and goes across and kind of just keeps on going in that direction. So our graph kind of takes on that look there, if you will. So kind of rough it out there. It's hard to do this on this little sketch pad, but that's the general idea of what this graph looks like. Again, you can use your graphing calculator and type these in and get a nice, clean, smooth graph on your graphing calculator. Our goal is to use our memory, though, not the calculator. So if I'm talking about the domain of this function, notice how there is not a left bound. There's arrows here, and there's not a right bound because there's an arrow there. So the domain, there is not any domain restrictions here. So the cube root actually does not have any domain restrictions like the square root did. The same way with range, the lower bound, again, is just an arrow, and the upper bound is still just this arrow. So there aren't any range restrictions. That's going to be from -infinity to infinity as well. Intercepts, again, it's only crossing the origin again. So we're seeing that quite often with a lot of our examples here, these parent functions. So the x-intercept is going to be this 0, and this y-intercept is going to be then this 0. Symmetry, again, notice how we had this point 8, 2, and this point -8, -2. We're starting to see this symmetry, again, going across the origin, those 2 points. So just like the cube function, the cube root function also has symmetry with respect to the origin. So the absolute value function is kind of a unique function. It's going to take on what we call a V shape. So it's kind of be more V-shaped. And this is the symbol for absolute value, these little vertical bars. And this symbol means how far a number is from zero. And this answer will always be a non-negative number. And that's why this thing takes on this special look. So when I put a -1 into this function, f of -1, this becomes the absolute value of -1. And what that's asking is how far is -1 from zero? Well, that would just be 1. And that's what we mean by the answer cannot be negative. It's going to be a non-negative number. F of 0, 0, how far is 0 from 0? Well, that would just be 0. F of 1, that means how far is 1 from 0? Well, 1 is only 1 from 0. Again, if I want to plot a few more, f of 2, you're going to say how far is 2 from 0, and that would still just be 2. F of -2, how far is -2 from 0, and that would also be a +2. So again, our goal is to just use these 3 order pairs. So -1 went in, 1 came out. 0 went in, 0 came out. 1 went in, 1 came out. So the answers have to be non-negative numbers. So the y value will never be negative. So if in graphing this, we have our order pairs. We have this -1, 1. I also had that -2, 2. You can kind of see that. 0, 0, 1, 1, 2, 2. You kind of see a pattern there with this. So that's how it kind of takes off and goes off in this direction. And then it also does the same thing over here. It kind of goes off in that direction as well. So it takes on kind of this V shape. So looking at this graph, again, this is the absolute value function, and it's going to take on this V shape where, again, it starts at the origin and it V's off in each direction. So it's going to be a rough sketch of it there. As far as the domain goes, notice how the left bound is an arrow and the right bound is an arrow. So there is not any domain restrictions. So -infinity to infinity. The range is, again, we're talking about the lower bound, but notice how there is a lower bound here, but the upper bound is still these arrows. So the lower bound is that y was being 0 over here. So the range value, the lowest it actually goes is 0. So I have to use a bracket there to say I'm including 0. And it goes up through infinity. Intercepts, again, we are using that origin again as the point of intersection. So this spot right here again is where they cross the x and y axis. So this is this x line and this is this y line here. And we kind of see that they both touch at that spot there where x is 0 and y is 0. So the x-intercept would be 0 and the y-intercept would also be 0. As far as symmetry goes, notice how we have these mirroring across the y-axis. So you have this point at 2, 2, and you have this other point -2, 2 as well. So notice how the x values are getting reflected across the y-axis. So the y value is not changing, but if you have a 2, 2, there has to be this x is -2 and 2 on the other side of the y-axis. So we do see this y-axis symmetry here. It is reflecting over the y-axis. The reciprocal function is a unique function. Notice that x cannot equal 0 because of the division error, division rule. You cannot divide by 0. So notice how x is in the denominator, x cannot equal 0. But to get 0, we also got to pick up on this, is that notice how you have 1 over x. I'm sorry, 1 over x. That's not what I wrote. So if I have 1 over x, another thing I have to pick up on here is the only way this can equal 0 is the numerator has to be 0. But the numerator is 1. So what this tells me is this cannot equal 0. In other words, y cannot equal 0 either. Because remember, that's the output, the answer. So in this problem here, there's two things. you can't have a 0 in the denominator because you cannot divide by 0. But also to get 0, the numerator would have to be 0. And since the numerator is 1, y cannot equal 0. So we pick up on these two things as observations. So what happens here off the bat is when I draw this reciprocal function, there's going to be this boundary of the x-axis because x cannot equal 0. I'm sorry, y cannot equal 0. And we also have the y-axis is a boundary because x cannot equal 0. So when we graph this over here, the reciprocal function basically means to take the reciprocal of each number. So if I have 1/2, the reciprocal of 1/2 means to turn that into a 2. So what you have is 1 over 1/2, which is the same thing as 2. If you put a 1 in, the reciprocal of 1 is still going to be 1. 1 over 1 is still going to just be 1. If I put a 2 in, the reciprocal of 2 is going to be 1/2. So if you have 1 over 2, that's just going to be 1 over 2. So we have what's called the reciprocal function. So if I had, say, 1/3, that's going to turn into a 3. If I have 1/4, that's going to turn into a 4. Or if I have 1/10, that's going to turn into a 10. So as we get closer and closer to the y-axis, the y values keep increasing. So this graph is going to kind of take on, let me go ahead and plot a few of these points though before I start doing that. So 1/2, 2 would be here. 1/1 is going to be here. And 2 would be 1/2. So this graph is going to kind of take on this slightly U-shaped curve. So if I can try to do that. So it's going to kind of take on this look here. It's going to kind of turn and it's going to kind of run along this way here. So it's going to do that there. What it also does is all these points are going to get reflected over the origin. So notice that if I choose a -1/2, that's going to be the reciprocal of -1/2 is going to be a -2. If I put a -1 in, the reciprocal of -1 is still -1. If I put a -2 in, the reciprocal of -2 is going to be this -1/2. So what we pick up on is you have this -1, -1. -2 is a 1/2 and -1/2 is -2. So the graph starts to take on this look here. So it kind of does that here where it doesn't cross the x-axis, nor does it cross the y-axis. It kind of gets bounded by that. So that's what I mean by two slightly shaped U-curves in opposite quadrants. So there's going to be this U-shape in the first quadrant. There's going to be this U-shape in this third quadrant. And they run really, really close to the axes. So it's kind of a description of the reciprocal function. As far as the domain goes, this actually has 2 intervals. So notice how it does have a left bound, but notice how x cannot equal 0. And then there's also this right bound. So the way we can write this is we can say, hey, this is going to be -∞ to 0, but we can't include 0 in union with 0 to infinity. If I'm using set builder notation, it's going to be the set of x's such that x cannot equal 0. It's every number but 0. If I look at the range is going to be very similar. Notice how the lower bound is an arrow and the upper bound is an arrow. And then notice that the origin, we cannot have y equals 0. So if I'm using interval notation, we would say, hey, -∞ to 0 in union with 0 to infinity. Or again, I can say the set of y's such that y cannot equal 0 if I use set builder notation. Notice this does not cross the x-axis or y-axis, so as far as intercepts go, this has none. On symmetry, though, notice how it is reflected over the origin. This does have origin symmetry. So notice how we had this point 1/2, 2. And we had this other point, -1/2, -2. Notice how the x and y values both switched. And that puts us, this puts us across the origin. So notice how you see this point 1/2, 2 here, and this other point 1/2, -2 here. So notice how they are reflecting across the origin. So we call that origin symmetry. The greatest integer function is also called the step function. So when you see this notation f of x equals int x, this stands for the greatest integer less than or equal to x. So that's kind of what's going on here. So what this is basically saying is your answers have to be integers. So if I evaluate f of -1, so again, if I just draw like a number line up here, have 0, put -1, 0, 1, 2, 3, maybe put a few more points there. If I'm at -1, the integer that's less than or equal to -1 would be -1. If I want to evaluate -1/2, a -1/2 would be located about here. That's where -1/2 would be. The integer that's less than -1/2 would be to the left of it. That would also be a -1. So what happens is all the integers between -1 and 0 are going to fall back to -1. So when we start to sketch this, we see that we have this -1, -1, but all the answers until you get to 0 stay there. But when you get to 0, the greatest integer less than or equal to 0 would be 0. So that puts me up to this spot right here. And what's going to happen is you're going to stay on 0 until you get to 1. And when you get to 1, you're going to jump up to 1. And then you're going to stay on 1 until you get to 2. And you're going to put a 0 open circle there, and you're going to move up to 2. And then you're going to stay there, and you're going to create these little steps. So this is called the step function. So it's going to keep making these steps forever. That's what's tricky is I'm not drawing the whole graph here. I'm only drawing a part of it. So this graph actually continues off the screen. So when it comes to the domain, notice that there actually is not a domain because, I'm sorry, there is a domain. It's just, there is no left bound or right bound because remember, this thing is going to continue forever to the left. This is actually going to continue ever for the right. It's just going to make the same pattern over and over again. So this is a tricky one because you can't base it on the graph per se because we're only drawing a part of the graph. So the domain is going to be from -infinity actually to infinity. There's not a domain restriction. The range, on the other hand, is just going to be the set of x's. I'm sorry, we're talking about range. So the range is it's not really going to be an interval per se, as much as it's going to be integers. So it's going to be a set of y's such that y is an element of z, where z stands for integers. So remember, integers are these numbers, it goes like 0, then it goes off to the left, -1, -2, -3, ... and it goes off to the right, 1, 2, 3, ... Those are what we mean by integers. And the capital letter Z denotes that. So that would be one way to do it, or you can just, just list the integers in that format there. So that's what the range is going to look like, is it's actually the output values are just going to be integers. So that's what we're kind of getting here. When I put 1/2 in, that would take me back to 0. When I got to 1, that would take me up to 1. And that's what we're kind of seeing here in our step function. So it stays on the smaller integer until you get to the next integer, then it jumps up. And it stays on that until you get to the next integer and it just jumps up and creates these steps. So that's what we call the step function or the greatest integer function. So those are the functions that you will get more familiar with as we move on. The next we get into is what we call piecewise functions. So piecewise kind of means a function is made up of individual functions. So a piecewise function, it can be represented by different functions. The catch is these different intervals of the domain. So notice this function here only exists between -3 and not quite 1. So that would be its left bound, and 1 would be its right bound, but it's an open bound. So, but when I get to 1, I have to use the new function of 2. And if I get to a number greater than 1, then my graph turns into this square root of x function. So the first thing it says, what is f of -3? To find f of -3, notice that x is greater than equal to -3 is over here. So that means -3 is included in this interval, which means I got to be using this function right here. So f of -3 is going to equal then -3, I replace x with the -3 and add 1. Well, -3 times -3 is a +9, and plus 1 will make that a 10. So f of -3 would equal a +10. So again, the -3 was your domain value, and the 10 becomes your answer or your range value. If I want to evaluate f of 1, notice that f of 1 is when x equals 1. And notice that when x equals 1, the function's it's already determined. It's that constant of 2. So f of 1 is just going to be that 2. F of 4, notice that you have to use where x is greater than 1 because 4 is greater than 1. So you got to use the square root of 4, and the square root of 4 becomes then this 2. So next thing says locating the intercepts. For me, to really understand the intercepts, I have to graph this thing a little bit. So what I pick up on to start with is -3x plus 1. That represents a line. But the only part of the line I'm going to graph is between -3 and 1. So remember, to graph a line, all we need is 2 points. So I'm going to use this information here to find those endpoints. So that's how we already evaluated -3. That was 10. So -3, 10 would be one of the points here. So -3, 10 would be here. And when I put 1 in, that's going to be -3 times 1 plus 1. That's going to be -3 plus 1, which is going to be a -2. So another point that we have to pay attention to is the 1, -2. 1, -2 would be here, but notice that that's actually going to be an open bound. We don't include it. So recognize that -3x plus 1 represents a line. So between these 2 points, the graph is going to take on this line look. And I can't really do that very well. Oops, let me get my eraser out. Let's undo that and try that again. So, all right. So we said this -3, 10 here. Let's see if I can use this other tool. Insert, we'll try to draw something here. So what I'm going to end up doing is drawing from here down to here would be my graph. So that's not bad. So notice that this is going to be one endpoint, but this other endpoint is actually going to be an open point because it's less than 1. So when I graph x equals 1, notice it's going to be a constant function of 2. So at that spot there, 1, 2 is going to be a spot on the graph. And then it says where x is greater than 1, we're going to graph the square root function. So remember the square root function, again, we have this 1, but remember we're not including it. Square root of 1 is actually going to be 1, but that's going to be an open circle at this spot. Now, if I graph, remember the square root function kind of opens up along the x-axis. So if I get one more point here, if I pick x to be 4, the square root of 4 is going to be a 2. So 4, 2 would be here. And there's also this 9. The 9 would be, the square root of 9 would be 3. So remember, the square root function kind of takes on this U shape and it kind of bends, but I have to stop here at this spot. So it kind of takes on this little curve up through here. Let me try to do that again. My hands is too shaky there. So don't really have a curving tool here. So try that again. Come in, breathe, and turn, and we have to stop at that spot. So we can't go past there. So that kind of takes on our graph from there. So based on the graph, we kind of see that there are three pieces to this graph. The first part's this line. The second part's this constant of just this one dot. And then the third part is the square root function. And that's what we see as these three pieces that we have to graph. So we did that. Now, as far as intercepts go, to find the intercepts, we kind of see that the x-intercept is here. So set it's on the line function. Remember, to find the x-intercept, we have to set y equals 0. So to find the x-intercept, we set 3x plus 1 equal to 0, and we solve for x. So 3x is going to equal this -1, x equals this -1/3, and that looks about right, -1/3. As far as the y-intercept goes, remember, to find the y-intercept, you have to set x equal to 0. So you have this y equals this 3x plus 1. I'm sorry, -3x plus 1. But you got to set x equal to 0 this time. So it's going to be -3 times 0 plus 1. That's going to be 0 plus 1, which is going to be 1. So we kind of see that, yeah, that makes sense because it does look like it crosses the y-axis at 1. So the x-intercept would be -1/3. The y-intercept would be a 1. And so that would be the intercepts that we could kind of see. They both come off of the line part of the graph. So let's look at one more piecewise function. So again, we have these three functions, and notice how we have these intervals over here. So this first function only exists between -3 and 0, and I can include -3. The -3 only exists when x equals 0. The x squared only exists when x is greater than 0. So the question says find f of -3. Notice that -3 is part of this first function. So I'm using the 2x plus 5 one. So that's going to be 2 times -3 plus this 5 to evaluate it. That's going to be -6 plus 5, which would end up being a -1. So the answer there would be a -1. F of 0, notice how x equals 0 would be here. So we're using the constant function, which means the answer is just going to be -3. No calculations to be done since it's that constant always. F of 2, notice that f of 2 belongs to the greater than 0 interval, since 2 is greater than 0. So I'm going to use the x squared function there. So 2 squared is actually going to be this 4. Again, to locating the x-intercepts, I really can't see that without really getting a better shot at the graph. So again, the first part is a line. And notice that it's going to be between -3 and 0. So let's just find those endpoints. So we already evaluated -3. We did that to start with, and that was -1. So -3, -1 would be the spot. Oops, no, -3, -1. I keep going up. So let's try that again. So -3, -1 would be actually down here. And then when x is 0, that's going to be an open interval. 2 times 0 plus 5, that's going to be 0 plus 5. That's going to be 5. So when x is 0, I get 5, but notice that that's going to be an open circle. So the graph is going to take on this line look between those 2 points. When x is 0, y is -3. So 0, -3 would be the other point. So 0, -3 would be down here. So that would be that interval. And the x squared function is, remember, it's that U shape. So remember, we have 0, 0, but notice that we can't include that. It's got to be greater than 0. We have that 1, 1 was another point. And we have like 2 squared was 4, and 3 squared was 9. So we kind of have this graph here. But remember, we can't graph the whole U because it says we only graph the part that's greater than 0. So the only part we're graphing is just this side over here. And it kind of turns, turn. There we go. That's not bad. So that's kind of going to be like the U-shaped graph that we see on this side. So we have a line, a kind of a dot, and kind of half of the U as our 3 pieces. As far as the x-intercepts go, I do see it cross the x-axis. It looks like it crosses the x-axis somewhere over here, somewhere. So let's set y equal to 0 and solve for x. That's going to be 2x plus 5 is equal to 0. Because remember, to find the x-intercept, you have to be solving for x, but y has to be 0 to do that. So we get this 2x equals this -5, x equals this -5 halves. And that's the same thing as -2.5. So that's what this point should be, is about -2.5. Not bad. The y-intercept we kind of see clearly is -3. So I really don't have to solve that one. It's just that -3 there. So that would be my intercepts there. So we got our graph and the intercepts there. Okay, so again, another thing you may have to do is an application. So I have a monthly tablet plan costs $34.99, which includes 3 gigabytes of data. It charges $15 per gigabyte for additional gigabytes after that. So the first 3 are kind of free. Well, I mean, they're $34.99, but after that, there's this extra charge of $15 per gigabyte. So the following function is used to compute the monthly cost for a subscriber. So we have this function. It's a cost function where C represents cost, and X is going to be the number of gigabytes involved. So if I want to compute the monthly cost for the following, we have 3 as the first one. So notice that 3 would be under the original plan. So that's only going to cost me this $34.99. But for 15 gigabytes, notice how that's going to be greater than 3. We have to use this formula here. So it's going to be 15 times 15. And then we're going to subtract this 10.01. So 15 times 15 is this 225. And then I got to subtract 10.01. So that's going to be 225.00 minus 10.01. Well, I can't subtract there, so I got to borrow, but I can't borrow from that. That's got to turn into a 4. This has to turn into a 9, and this becomes a 10. So 10 minus 1 would be 9, 9. 4 minus 0 would be 4. 2 minus 1 would be 1, and a 2. So 214.99 would be that answer. Okay, so that makes sense, $214.99. So that kind of jacks up the bill quite a bit by doing that. So that's what you may have to be doing in your homework as an application problem, something like that. And again, you have to pay attention to the domain, the interval, to determine which piece of the function you use. Well, I'll stop there, and hopefully you got something out of this, and we'll move on to the next lesson here in a little while.